Okay, here we go. Okay, what do you got? Yes. 57, please. So 230, 57.
No, I did it with you, and you were like, I don't understand.
Oh, inverse secant of 1 over t? Okay.
No.
Okay. Well, let's take a look. I'm not quite sure what the issue might be here with, but we'll figure it out. Okay. And make sure I'm on the right page. Is it inverse secant of 1 over t, right? Okay. Okay, and they are saying something about 0 is less than t is less than 1, which I don't know if that'll come into play, but I'm going to write it down anyway before I flip it to the back here. And secant, let's go ahead and just write the formula. I'm just going to write the formula and plug it in at the same time. So I have 1 over 1 over t square root of 1 over t squared minus 1. And I've got to take that times, so that 1 over t equals t to the negative 1. So that'd be negative 1 times t to the negative 2. Okay. Technically, the reason why they are throwing in the fact that 0 is less than or equal to less than t is less than 1, this is something I haven't discussed, but we're not gonna worry about it at all. There's an absolute value here, because if x was a negative of some sort, they want this to be positive. In this case, t is positive, so 1 over t is positive, so we don't have to worry about that at all. Okay, so here we go. I'm going to go ahead and just keep my negative up top. My guess is it was, how did they simplify it? Where did their simplification come from? So I'm just going to take this t to the negative 2 down bottom times 1 over t square root of 1 over t squared minus 1. So negative 1 over t square roots of 1 over t squared minus 1. And whether or not we simplify what's underneath, I suppose that's kind of up to us. I'm going to go to the side so I don't have to widen out too much more. Did they find a common denominator under the radical or not?
No.
Okay, so they just simplified this right here? Okay. Is that what they've got? Good.
They have, it's negative 1 over the square root of 1 minus t squared.
Okay, so they did simplify it. Okay. So let me go ahead and continue working with it a little bit and see if we can come up with the same thing, kind of give us some confidence that we're doing these things correctly. Well, let me get rid of this circle because I thought I was done. Oh, okay. I know where they're coming from now. And I see the reason for simplification. Do you see where that other t canceled from? Because once we find our common denominator, my common denominator is t squared. I can take the square root of the top, which would be square root of 1 minus t squared. Square root of the bottom would be t, and that'll cancel out with that t. Please tell me I'm good. Okay. On the most part, going all right? 63. 63. I'm trying to get better at my Spanish. And I know that's not right. I know very little Spanish. Wish I knew more. And I didn't mark where my book was. Urgh. Derivative of t? Oh, yes, by e to the derivative of my nested function here, which is, let's see, e to the t. What's the derivative of e to the t? Oh, that's right, it's e to the t. I always forget that one. Okay, so what you're going to see is my e to the t's cancel. So I'm going to be left with the square root of e to the 2t minus 1.
But I feel like the answer is so much longer than that.
No, it's like they didn't simplify it. They didn't cancel it.
Really? This is where what I was talking about before. Sometimes they're like, okay, we're going to simplify this like crazy. Other times they're like, yes, Melissa.
Oh, it leaves it both ways.
The formula. It's just the formula.
They did it both ways. They have a simplified version equals the unsimplified version.
Oh, okay. Okay.
I was just so confused. I think I saw the e to the t, and I was like,
Okay. But I'm glad we did that one because it really highlights that we focus on whatever is here, and then we got to take the rate of change of that. Okay. And actually, that's one of the reasons why this book actually likes to write this formula or all these formulas like this. And this is going to come back and benefit us a little bit later. Negative 1 over absolute value of u, square root of u squared minus 1 times du dx. That's why sometimes they write it like that, to emphasize the fact that whatever's here, don't forget to take the rate of change of that. Okay, but if we just have our radar open for chain rule, then we'll be good to go.
61 says there's like 2. How do you do that one?
61 says there's like 2.
There's like 2.
there's a log and a...
Okay. Oh.
61. Sorry.
Yeah.
There's like 2, whatever it's called.
Okay. Well, I'm glad we're doing a natural log because that's something we kind of glossed over a little bit. Remember that the derivative of natural log of x is 1 over x. Okay? So let's do 61. Okay, so let's go to my formula. First of all, the derivative of the outside, 1 over times, and then I'm going to have the derivative of tangent, or inverse tangent, 1 over 1 plus x squared. Is that what they have for an answer?
Yeah,
Oh, yeah.
Oh, okay.
it's like 1 over.
Okay.
I just wrote it down. I just wanted to know how to get there.
Yep. So it's the outside function and then derivative of the inside function. Yep. Okay. So let's take a look at our related rates issues. Where am I at here? I asked you to set up number 2 and number 5, right? Okay, that'll be a perfect little transition to today. 2 is a good review. 5 is a little extension to a harder problem. Okay. Okay. So gathering our information, I think that's really very, very straightforward in this one. We've still got our R, and that's it. So now what we've got to do is find out, okay, there's my dA dt, there's my dr dt. I want to relate those to A and R before I differentiate. So A is equal to pi r squared. Or should I plug in 10 for R? Not yet. I've got to leave it in terms of a variable, then differentiate, because is my radius always 10? No, so I cannot include it right here. I've got to go ahead and anything that's going to change, leave it a variable. Okay. And now, because actually the thing that I think is kind of neat to think about with these problems is as I drop water on the floor, or oil, or whatever, describe what happens to my radius. At the beginning, is my radius changing fast or slow? It's changing pretty quick, isn't it? But then when the circle gets this big, is it changing very fast? No. So so you can see that it depends upon where you are in the time. Okay. Okay. So let's see. dA dt is 9, so I'm going to go 9 pi is equal to 2 pi r. Well, but my r is 10 now, so I can plug that in. And then I'm left with dr dt. So that's where my variable sits. Okay. Nine twentieths or 0.45. But what would my units be? There you go. Go back to the beginning. Meters per minute. Okay. First of all, give me a thumb scale on how something like 2 is going. Okay, good. 5 is a little different ballgame. 5 was designed, the reason why I just had you guys set that up is because this one's going to be a little bit more of a challenge to come up with an equation. Okay, the last one's just area. The previous one's area. And 6 was just Pythagorean theorem. 5 is a little bit different deal. A person's walking away from a 20-foot tall lamppost. Okay, so here's my lamppost. The only thing you'll ever see from me is stick people, stick dogs, and stick cats. Okay? So it's hard to differentiate between my stick dog and my stick cat, but, usually it'll be in the problem. Anyway, so 7-foot tall person. Wow, that person's tall. Did I ever tell you about the time that my basketball team was getting ready to play up against a 7-foot tall guy in high school? Where they gave me the sticks to extend my hands. That was so much fun. Such a fun week. First of all, can I label that as 7 or should I leave it like height? Yeah, because it's always going to be 7. Okay? So it says, assume the scenario can be, I was walking away. So the speed right here is 5 feet per second. Okay. and they want to know, assume, at what rate is the length of the person's shadow. Well, let's go ahead and get some things figured out here. Okay, so we got the shadow right here. Okay, so let's throw in a couple variables. They want to know the length of the person's shadow changing. So they want to find ds dt when they're 16 foot from the lamp post. Well, I don't have that. I don't have a variable listed for that, so I probably should. Okay, so let's call that x. And we're going to call the length of the shadow s. Okay. So it says 7 foot tall person is walking away at the rate of 5 feet per second. So what is 5 feet per second in terms of all of these variables? It's how quickly x is changing, right? Okay, because as I'm walking away, my x is growing at 5 feet per second. So, so I know that dx dt is equal to 5. Okay, so even just to get to that's a little bit of a challenge. Okay, we don't have an equation relating everything yet, but what I have is I've got a shadow and this distance here. I could maybe have called this something, but that's going to make it a little bit more complex because the shadow plus this distance here is not changing at 5 feet per second. Okay, it's just this distance here that's changing at 5 feet per second. So we're going to kind of not do that. Okay, so if we go back to kind of our whole philosophy on this, now we have to relate s and x. X plus s. What about x plus s? Okay, x plus s is this distance right here.
Can you still control it?
I could, but this angle's going to be changing. So then we're going to add another thing that's going to change into the mix. And that's just going to make our lives a little hideous. Proportions. You see the two triangles? Those two triangles need to be in the same proportion. Why? Because they share the same angle. Okay, and they both are a right triangle. Okay, so x plus s relates to what? 20, okay? And in the small triangle, what are those two sides that correspond to that? Get your order right. So bottom is to height as bottom is to height. There you go. There's our equation that relates everything. Okay? Now, I'm not too hip on and this is something that's going to take a little practice. There's no doubt about it. Okay? That's why I didn't assign 5 to get totally done. I'm like, just set it up. Okay, I'm not too hip on differentiating this right now. We can go ahead and simplify this as much as we want. So let's do that. Okay? Okay. 20s equals 7x plus 7s. 13s equals 7x. So there we go. So there's my equation that's going to relate the two without x being something specific, without s being something specific. So now we're going to have to do what with this? Differentiate. Okay? I'm just using all my colors today. I'm feeling colorful as I wear all black because it's test day for Algebra 2.
Trying to scare him?
No, the information will do that just plenty. No, it's actually today's not too bad if they've been doing what they should. Okay, so what's the left side if I differentiate? 13 ds dt equals 7 dx dt. Okay, so let's plug in. My ds dt is what I want to know. Something doesn't feel right here. Can I just take a second? It really feels like something is missing.
Because that's 16 divided by x.
Yeah, but maybe it's telling us that the where it is, it doesn't make a difference, because maybe my shadow's always growing at the same rate. Okay? I do have the answers here, so I can double check that, but that's why I'm trying to model it when something doesn't feel right. Just step back, take a deep breath, and let's problem solve. So my s, and this is x, and this is x plus s. S over 7, x plus s over 20. Let's simplify that. So then when I differentiate that, it is going to disappear. Okay. So I'm going to move forward with some level of confidence, because the math usually tells us some things as we go. So ds dt, I don't know what that is. 13 ds dt equals 7 times 5. And ds dt equals 35 over 13, which 2.69. 2.69 what? Feet per second. Okay.
So,
Yes, ma'am.
on that one, where did like the 16?
16. It may be and I'll do an example here where maybe I can't think of one off the top of my head, but sometimes your rate of growth or your rate of change is constant. It doesn't matter where you're at in the situation. Like in our circle, yeah, that's pretty obvious. It's going to change. But maybe in this situation, what the math is telling us, at least what I'm seeing, is that it doesn't matter where you're at. It's always going to be growing at this rate. Okay? Yep, and we are correct. But that's a great question, because intuitively, that's why I stopped and I took a deep breath. I'm like, wait a minute, shouldn't there be an X I got to plug in somewhere, and I got to find the S? Nope, it doesn't matter. Okay? Okay, while we are on that particular problem, let's go on to something that's very similar. Okay? Let's go to number 3. Conical paper cup is 10 centimeters tall with a radius of 10. Cup is being filled with water, so the water level rises at a rate of 2 centimeters per second. At what rate is the water being poured into the cup when the water level is 8? Okay, so we've read it once. Now we're going to read through it again. I'm going to go ahead and draw a picture. Okay, I can label both of these because they don't change. Oh, I'm even going to go to watercolor. Okay. So there's our picture, and a lovely picture it is. I got to be honest, I've never really used much colored pens in my teaching before, but this is one of the things they gave us at this meeting we went to a couple weeks before school started, and I just love this. I love it. I mean, it's just like, it's awesome. I reached out to the person who put the whole thing together, and I sent him an email that says, hey, thank you. I think that was the best part of the whole thing. And I never heard it back, so maybe they got it, maybe they didn't. I have no idea. Or maybe they just don't like me and decided to delete the email before they even read it. Okay, so this cup is being filled with water so that the water level rises at 2 centimeters per second. So what do I write? The height is 2 centimeters? Not dH dt is 2 centimeters per second. So it is growing at the rate of 2 centimeters per second. At what rate is the water being poured into the cup when the water level is 8? So it says, at what rate is the water being poured into it? So what do they want? dP? Let's find a better variable than P. If we're pouring it in, what are we changing? We're changing the volume. The rate at the volume is changing when, that's the ugliest V, when H equals 8. This is a tough one. Okay? But it relates a lot to number 5. Okay, so what I've got to do is I've got to write an equation relating height and volume. Okay, volume of a cone. Anybody remember the volume of a cone? Not half.
Is it like 3/4 pi something?
Volume equals 1/3 pi r squared times its height. Here's the way I remember this, is that pi r squared h is the volume of a cylinder. And this is going to be a fraction of that. It's 1/3. Both pyramids and cones are both 1/3. Okay? So I've got V and I got H. Do you see a problem? I've got an R here. That if I differentiate right now, I'm going to have a dr dt. I have no idea how fast the rate of the radius is growing. I don't know what the radius will be, but what? Oh no, the 10 is the whole thing. This is this little radius right here. Okay? So this is kind of a trick, and I doubt you guys would see it. Not trying to minimize your skills here or anything, but check this out. Does that look familiar? It's a proportion. Okay? So here's the thing. What I really want is I want volume just in terms of height only. I don't want an R. So to get rid of my R, I need an R equals and something in terms of H that I can substitute. So what we have to do is we have to relate these two things. Write an equation relating R and H. Over here, write an equation relating R and H. Go. Proportions. Go. Small triangle, big triangle. It's not overly challenging proportion. It simplifies really nice. Thank goodness. Okay, so what's my proportion? What over what equals what over what? 10 over what? 10 over 10. Okay, so my radius over my height equals R over H. There we go.
So you just solve for R?
Yeah. If we cross multiply, well, we can actually replace this with 1. So, but, you know, I don't know. If you cross multiply, you get 10R equals 10H. So R and H are the same, which is kind of rare. Usually we've got to take that H is like 3H or something, and we'd have to plug that in for R. So this one's telling me, what can I plug in for R? H. Okay. Can you see why I have 3 days planned for this? Yeah. Okay. So now what we've got is we finally have this relationship between V and H that I want, and now I can differentiate. Go for it. Differentiate. I'm going to come back up to the top so I leave myself some room, but okay. Let's check. Are you here?
What?
Where dv dt equals pi h squared dr dh dt.
Okay, I just listened.
You there?
Yeah.
Okay. So now what do we do? Plug things in. After you differentiate, then the gates of substitution are open. You can go ahead and put stuff in. But then we need to think about units. 128 pi, what?
Centimeters cubed.
So why centimeters cubed? Because it's volume. Good. Tay's having a great week, aren't you? She's on top of it. Per second. So now, I'm actually going to go back and do some dimensional analysis and make sure we're right. 8 is centimeters. 2 is centimeters per second. So centimeters squared and other centimeters gives me centimeters cubed per second. Here we go. So we're golden. Okay. Okay. One more. And I'll just pick a 2 or 3 from the book after this. A spherical balloon is inflated, so its radius increases at the rate of 2 over r centimeters per second. Okay. Okay, you know what question's coming next. Do you remember the formula for volume of a sphere?
The opposite of the circumference.
Oh, opposite of the area thing. Okay.
It's 4 pi something.
4/3 pi r to the third. Okay, go ahead, differentiate, plug it in, find dv dt, get your units right. You can leave it in terms of pi if you wish.
If it's a 2 over r, we just move the 4 and drop it.
Mm-hmm. Yep. The question was, if you have the 2 over r for my dr dt, should you plug in the 4? Just since Jesus probably couldn't hear that question. Jesus is probably wondering what I'm waiting on, because when I pause this, it doesn't pause it on the recording. So it just shows me doing work. Okay, what'd you get?
32 pi.
32 pi? Oh, I forgot to square. You had me there for a second. 32 pi centimeters cubed per second. Good job. I wish somebody would have asked that.
Hey, I didn't click in my brain at first until you said it here. I was like, oh, wait a minute.
Wait a minute. I've got to. Okay. So this is a good sheet for. First of all, I'm thrilled with this worksheet. I'm going to make sure and put that in my file for next year. And then so this would be a good reference. So let's pick a couple problems from the book and let's see how you do. Okay? April, pick a number between 4 and 7. Yeah. 6. Okay, that's how many problems we're going to have. No, I'm joking. I've got my go-to number I pick also every time. So. Ooh, I like this one.
Yeah, that made it sound.
A little evil. That is freaky. I forgot that I had actually selected this assignment a few days ago, and I just selected a new one. They're the same. That's weird. What are the chances? Okay, let's stop this.